2 3 minutes. After that, I will start. Okay. So this is the eighth week problem solving quiz on advanced atmospheric physics. Okay. So this plan is the same. We will discuss first the assignment 7 question, and after that we will move towards the week 8 content. And in the week 8, what I have seen is that uh, you will get first the thermal winds and the gradient wind balance using the natural coordinates, and after that you will go towards the ionosphere part. Okay, so we will see one by one. Give me a moment. Okay, so let's see the week 7 assignment questions. So it says that if increase in pressure is 10 hectopascals throughout a distance of 100 kilometers eastward, what will be the geostrophic wind speed? Assume that density rho is equal to 1 kg per centimeter cube and Coriolis parameter is this. First of all, this will be this rho is equal to 1 kg per centimeter cube is not the right path, which I have already told in the last session, that it should be 1 kg per meter cube. Then only you will get towards the answer. Otherwise, it will be very deviated one. Okay. So So if increased pressure is 10 hectopascal through a distance of 100 kilometers eastward, what will be the geostrophic wind speed? That is the simple question. So we know that if your pressure gradient is in, say, x direction, that is eastward direction, which is east, this is west, and the distance between them is 100 kilometers. Here it is suppose P naught, and as you go towards the east with 100 kilometers, it becomes P naught plus 10 hectopascal. That is what is given in the question. Then where should the geostrophic wind go? It should go like this. It will be parallel to the gradients, the pressure gradients, right? Pressure surfaces. Okay. So this is the geostrophic wind. All right. Now, the next thing is that, so suppose this is your Vg, that will be 1 upon rho f delta p delta f. Okay. So rho is given to be 1 kg per meter cube. It's not centimeter cube. Cc is not right. That is the question's problem. So F we know, which is about 10 to the power minus 4 per second, right? So everything mostly we know. Now, if you do couple of things, couple of calculations, if you just put these things, you will easily get the answer. So Vg will be equal to 1 upon 1 into 10 to the power minus 4. That is rho and f I have just put into this particular equation, and delta p and delta x. Okay. So delta p in the eastward direction is given as 10 hectopascal. I have to convert it into the pascals so that I get the SI unit, right? So 10 into 100. That will be in pascals. And what about delta x is 100 kilometer. So which is 100 into 10 cube meters. Okay. So Vg will be equal to 1 upon 1 into 10 to the power minus 4. Delta P delta x will be this divided by 100 into 10 cube. Perfect. So this is what you are getting. So Vg, therefore, it will be, say, the 1010 cube goes. So what you get? 1 upon 10 to the power minus 4 into 10 square, which gives you 1 upon 10 to the power minus 2. That will give you 10 square meter per second, which will be 100 meter per second. Okay, so this is how you will get, right? So, this is the question, and we have got this particular answer. Now, the thing is that if you visualize this particular question, see, Coriolis parameter is 10 to the power minus 4. What is Coriolis parameter? Coriolis parameter is 2 omega sine phi, right? We know f is equal to 2 omega sine phi. Now, phi in northern hemisphere is always positive. So when you have given this f is equal to plus 10 to the power minus 4, that means it is in the northern hemisphere. Correct? This is fine. So if it is in the northern hemisphere, then where should the geostrophic wind will be? We have discussed it in the last session. That is, if you have a low pressure isobar and there is a high pressure isobar. Okay, there is a pressure gradient. Then where should or which direction should it move? It can be this or this. Which direction it should move? It should move this. So that to its left in the northern hemisphere, you will get the low pressure isobar. Understood? So this becomes the direction of VV, not this. And similarly, here also see it is coming out to be positive 100 meter per second. That means northward. See, this is northward. And as it moves northward to its left, see, to its left, the pressure is lower. That is what I am trying to show. Okay, so not only that you have to answer the question, but you have to understand that how the things which have been told whether these are perfect or not. Okay, so this is one of the things. Just a minute. Let me give me a minute because here in that Google Meet, they're saying that time issue is there. So just check out. See, I'm giving you the new link. Okay, just note it down. If in any case this link expires after 1 hour, then we can join this link in the chat box I have given. Okay, just note it down, particularly the codes, the UDZ, VEIN, and QW. Okay, then we can, if within 1 hour it expires, then we can go to this link. Okay, for the time. Fine. Okay, so this is the first question. Yeah. Okay, please, because I don't know suddenly today this is happening. Okay, let's go to the next question. What is that? Yeah. Okay, so this is 100 meter per second. Perfect. Next is, what is the geostrophic wind for a height increase of 10 meter or 200 kilometer of distance toward the east? Assume FC, the Coriolis parameter is 10 to the power minus 4 per second. Okay, so how will we proceed this question? It's a bit simple. So, what it says, just read the question. Geostrophic wind for a height increase. See, remember, when we have done in Cartesian coordinate, that is x, y, z, t. So here, when you have vertical coordinate at the z axis, we have got the Vg as what? 1 by rho f delta p delta. Okay, I'm not writing this. This is the meridional component, suppose. Okay, but we have also seen that in the pressure coordinate system, the same Vg, the meridional, suppose, is 1 by actually f delta phi by delta. What is phi? Phi is the geopotential, right? Geopotential. And what is the definition of geopotential? G times the geopotential height. This is geopotential height. Understood? So now when we write, particularly for this question, it actually says that calculate the geostrophic wind when you see that your geopotential height changes as we go in the x or y direction, whatever is given. Okay, so my expression therefore, suppose Vg becomes now 1 by f, g can be taken outside, delta z by delta. This is your Vg, and your Ug will be similarly negative g by f delta z delta. All right, this is for the xypt coordinate. We calculate the geostrophic wind. Okay, so now it is given that your delta z eastward it is given. So delta z by delta x. Okay, delta z by delta x. Okay, just one thing. Uh, this my Google Meet, this particular link might expire in 1 hour. So I have given in the chat box one link. So if it expires, then try to see this link. Okay, join after 7 o'clock. Okay, just information. Okay. So delta z delta x becomes 10 meter given whatever given. Okay. Then 200 into 10 cube meters. That's in 200 kilometers, 10 meter is the change in height, geopotential height. This is given from the question. Now you can easily solve, and you know that which component of geostrophic wind needs to be calculated? Of course, this. Because delta z delta x is given. This is not given. So we will not calculate that. All right. So Vg, therefore, will be G by L and delta Z by delta X. Perfect. Now, this becomes then 9.81 divided by 10 to the power minus 4 into 10 divided by 200 into 10. Perfect. So now, just do the calculation. I think it will come out to be about 4.9 meter per second. This should be the answer, right? And since you are getting the positive value, then what will you say that about its direction? Direction will be northward. All right. So this is what simple question. Just the trick is that you have been given instead of pressure gradient, you have been given the geopotential height gradient. Perfect. So this is what you have. So let's go to the question again. See, 4.9 meter per second is the accepted answer. It is towards the north. Okay. Yeah. Third question is a bit tricky question. So we will keep it for the last. Let us discuss the other ones. This is also a good question. Let us first discuss the fourth question. We will come to the third question last at last. So the fourth question is, what is the divergence of geostrophic wind at 45 degrees north at a point where Vg is 50 meter per second? So let's do that. It is asking for fourth one, right? It is asking for the divergence of the geostrophic wind. Okay. So how will we calculate the divergence of the geostrophic wind? I have already shown you in the last session that suppose you have your Vg, which is nothing but minus 1 upon rho s delta p by delta y I hat plus 1 by rho s delta p by delta x j. This is your question because this will be your the zonal geostrophic component, and this is your meridional geostrophic component. And you know the meridional and zonal are proportional to the opposite gradients, right? So this is what how you can write. What we need to find out divergence of geostrophic. So how will we calculate divergence? Simple. Divergence means this, right? This dot product with the VG. I'm not writing the entire expression again. So how will we get that? So it will be del x of minus 1 by rho f delta p delta y. Correct? UG will come plus del y of 1 upon rho f delta p delta x. All right. Now, see, this Coriolis parameter f is not a function of x, right? Because why? Because f is equal to 2 omega sine phi. Phi is the latitude. And latitude variation happens where? In the y direction, not in x direction or z direction. Therefore, f is a function of, so f is a function of y, not x. All right. So this is what you get. Now, so minus, so since f is not a function of x, rho is constant, so you can keep it out and put this, a double derivative, plus 1 by rho can be taken outside, but Here is the trick. F is a function of y, so it has to be differentiated. So one term we can write that it is 1 by f delta square p by delta y delta x, and the other term will be delta p delta x will be as it is, but you have minus 1 by f square delta p delta sorry delta f delta y into delta p delta x. This is what you will get. So finally, what your answers will be is this, right? Delta x delta y plus 1 upon rho f delta square p delta x delta y. You can write it like this. And finally, minus 1 by rho f delta p delta x into 1 by f delta x by delta y. All right. So just look into this particular expression. This is important. What we can see is that the mixed derivatives, that is del square p upon del x del y and del square p upon del x del y, these things will easily getting cancelled, right? Only thing left is minus 1 by rho l delta p delta x multiplied by 1 by f delta f delta y. All right. So f square I have just written it like this. Okay. So this you can cancel, and finally you get it minus 1 upon rho f square. You can write delta p delta x and c. We know that delta y can be written as radius of the arc times a delta phi. How? This. Suppose this is your radius of the arc. This is some angle phi. This is your y, right? So you can see angle is equal to arc upon radius. So you can write a delta phi. So minus 1 upon rho f square delta p delta f. So this can be written as delta f upon a. Oh, sorry. F can be written as now 2 omega sine phi divided by delta phi. Okay, this is what you are getting. Fine. So now I think one F should be should not be there. Or no, it's okay. Fine. Let it. So what you get is therefore see minus 1 upon rho f delta p delta x. This can be written as your Vg, the geostrophic field, and this, if you do differentiation, then what you will get? It should be about, I think it will come out to be cot phi by something like this. So this is your Vg, which is given to be 50 meter per second, and cot phi is 45 given in the question. So it is 1, then cos by sine. So cos 45 is 1 by root 2, sine 45 is 1 by root 2. So if you divide, you will get 1. Divided by the radius, that is 6370 into 10 to the power 3 meters. When you do all those things, you will get something like this, right? So if you further solve this, you get 10 to the power minus 6 percent. This should be the answer. But in the question, you will see that it is about 10 to the power 6. And I don't know why it is 10 to the power 6. I'm getting an opposite, 10 to the power minus 6. So this is one of the things which I'm not sure about. Okay, so this is how the divergence of geostrophic wind has to be calculated. When you are given that at 45-degree north, what it will be. Okay, just remember that f, the Coriolis parameter, is a function of y. It's not a function of x. So when you have a function of y, you should include it. Now when we write delta p delta y 1 by f and all those things for UG, we assume that f is constant. It's not there, but actually there is. Okay. Next is the fifth question, that is Steady state inertial motion. This is a हाँ हाँ हम्म हाँ 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 ओके 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 बता ओके अच्छा पॉइंट ऑफ व्यू सो ये यहाँ से ये देखा देखो इस स्टेप में क्या किया -1/ρf डेल्टा पी डेल्टा एफ सही बात कह रहा हूँ एक एफ होना चाहिए इधर और ओके डेल्टा 2 ओमेगा साइन फाई ए डेल्टा फाई यही होना चाहिए अब ये तो हो गया ये वाला पार्ट 2 ओमेगा साइन फाई डिफरेंशिएट अगर करोगे सो व्हाट इट विल बी साइन फाई का हो जाएगा कॉस फाई ठीक है अब एफ जो है उसको मैं लिखूंगा हाँ वही मैंने एक सॉरी वो स्टेप मैंने वो ये तो 2 ओमेगा 2 आ गया तो ये ठीक है ये अच्छा अच्छा पॉइंट आउट किया मैंने मिस कर डन नेक्स्ट इज द फिफ्थ क्वेश्चन that is steady state inertial motion results from. So inertial motion we have already discussed is a simple question. It's a just the balance between the Coriolis and centrifugal force, right? So your Coriolis force is a pseudo force, inertial force, and centrifugal force is also another pseudo force. And these pseudo forces are sometimes called as the inertial forces. These two balances to give you the inertial motion. This is fine. For horizontal flow to become geostrophic, what should be the Rossby number? See, for Rossby number, exactly when it is equal to 0, we have seen that it becomes geostrophic. So, according to me, it should be Rossby number equal to 0. But Rossby number less than 1 is also a kind of a geostrophic approximation. So, we can write Rossby number equal to 0 and less than 1. So these two, uh, according to me, are right. So I don't know what is the specific reason for Rossby number less than 1, but understand the thing that how we calculate. Okay. So this is the sixth one. So Rossby number, what is the definition of Rossby number? It was B upon RF. That was the definition of Rossby number. Right. So your F is the Coriolis and this B by R. So it's just like it comes from centrifugal to Coriolis. So if you go by this definition, so whenever centrifugal force is much less than the Coriolis force, that means the Coriolis force is important. Then you get Rossby number less than 1. And in that case, you get a geostrophic balance. And this we have shown when we have tried to do the scale analysis part. This Rossby number can also be defined like this: du dt divided by fv, and this gives you the same 1 upon rho s delta p delta x and plus 1. Okay, so if this is your Rossby number, right? So if this is your Rossby number, and I think there's some v will come somewhere. So I think here only the v will come. Okay, so you can see when Rossby number becomes exactly equal to 0, your v tend to become -1 upon rho s delta p delta x. I think this will be minus, this will be plus. Just check it once. Okay. So both are right. I think Rossby number equal to 0 is also right, but Rossby number less than 1 is also a perfect approximation. Okay. So this sometimes becomes confusing. Seventh question is Cycloscopic wind motion results from which of the following forces? So we know. So we have already seen this. The seventh one is cycloscopic balance. The cycloscopic balance is the balance of pressure gradient force and your centrifugal force. This happens when Rossby number becomes much greater than 1. Okay. So for that, this is the balance. So if you look at the question, pressure gradient, and so none of the above is the correct option because none of the options have this. All right. Next is the generic name for a wind speed measuring device. So wind speed measuring device is anemometer. This is very common and it is known, so I have nothing here. Let's go to now this question, the third one. Okay, third one is a bit deep question, so we need to understand. So let us do one thing. Let us first read this question. Okay, let us first read this question, so that will be helpful in understanding this. Okay, one thing, those who have joined somewhat late, uh, I have given in the chat box a new link. Okay, for the Google Meet because I think today it is showing uh, it might get expired after 1 hour, so at 7 o'clock. So just follow up this link. So let me, if I have to pin it, yeah. So just copy this link if it goes, and if you want to attend, you can attend using this. Okay, just and let me know if you haven't got the link. Okay, so third question says that two moving ships passed close to a fixed weather ship. Okay, so in an ocean there is a weather ship which generally uh, observes certain meteorological variables like temperature, SST, wind speed, all those things. That is a weather ship. Now, within a few minutes of one another. So, two moving ships are passing by this particular weather ship. Okay. The first ship was was steaming, it should be steaming eastward at a rate of 5 meter per second, and the second one was swimming northward at 10 meters per second. So first ship was going eastward, that is positive x direction, at 5 meters per second. Second ship again going in the positive y direction because northward at 10 meters per second. Now is the question. During the 3 hour period of the ships were in the same vicinity. All the three. The weather ship, ship 1 and ship 2. Within a 3 hours period, all these three ships are at the same vicinity. The first recorded a pressure rise of 3 hectopascals, while the second recorded no pressure change at all. Fine. During the same 3 hour period, the pressure rose 3 hectopascals at the location of the weather shape, which is at this point. On the basis of this data, calculate the geostrophic wind and direction at the location of the weather shape. So, geostrophic wind you have to calculate, and geostrophic wind velocity is a vector quantity. Okay, so this has to be done properly. Let us list down, you can say long question, and it's better to see how we can solve this. This is the third one, right? Okay. So, what has been told to us that there are three ships. Perfect. So, let us see what given conditions are there from the question. Okay. So, there is a ship one, is that u is equal to 5 meter per second. This is the ship's velocity. Just remember, this is the ship's velocity. Next is delta P. What the ship one has seen that your delta P in 3 hours period has increased 3 hectopascals. Correct? In 3 hours of period, the delta P for the ship one is 3 hectopascals. All right. Now, what about ship two? Ship 2 was swimming northward. Northward means positive at a rate of 10 meters per second. And it has noticed that the pressure in 3 hours of period changes zero. So 0 hectopascal in delta T is equal to 3 hours. This is what is given in the question. And there is another shape which is the weather shape, which gives you the local observation. Local observation of pressure. P is the pressure. Just to note. What it has observed? It has observed that the pressure has rose 3 hectopascal in 3 hours. Now, what we should use? There's so many information which is given here, right? What should we use? According to me, we should use simple total derivative expression. dP is what? Delta P plus V dot grad P, right? This is what we generally write. And let us assume for the time being that your vertical velocity is zero. So it is perfectly horizontal. So horizontal advection. Perfect. This is local change. And this is the total change. Which one will give you the local change of pressure with respect to time? Of course, the weather sheet, because weather sheet is stationary at a point and it is taking the observations. So delta T, which represents the local change, will come from the weather sheet. All right, will come from the weather sheet. What about the total change? So let us now do it. So for shift 1, your dP is increased 3 hectopascals in 3 hours of time. All right, this is your dP for the shift 1. So I'm writing like this. So apply this for shift 1. So it will be what? dP is equal to delta P plus U delta P delta X, because the shift 1 has moved only eastward, no, not Y. So V is 0. V is 0. So this becomes 3 hectopascals by 3 hours. What about local change? The weather station, whatever it has noticed. Same. U, the ship's velocity, 5 meters per second, delta P delta X. B. So this gives you 1, this gives you also 1. Remember, this is in hours. So it will be 1 by 3600 actually. Okay. So just be careful. So, okay. So then this is 1 and this is 1. Anyway, these two will cancel and it gives you delta P delta X equal to 0. Correct? Because they are the same, right? So delta P delta X will be 0. From sheet 2, if you apply now dP for the sheet 2 is 0 hectopascals in 3 hours. In that case, again if we apply this, it will be this because it is moving only northward. Okay. For the second shift, this is 0 hectopascals because it has been no change in the 3 hours period. But delta T is the weather shift observation, which is X plus B delta P delta Y. And what is B? 10, positive. This is 0, fine. So it will be minus 1 hectopascals by 3600 is equal to 10 delta P delta Y. Now, hectopascal. Can we convert it into pascals? 3600 to 10. This 10 I am bringing in here. Okay, this is minus. Perfect. So what I get? Minus 1 upon 360 is delta P delta 1. So in one case, we have got delta P delta x equal to 0. In the second case, we are getting delta P delta y is equal to minus 1 by 360. Now can we calculate the geostrophic wind? Yes, because for geostrophic wind, what we require is the pressure gradient. And we have got it. Now, what is the latitude at which all these things are happening? Let's see where the weather ship is. Because all the three ships were in the vicinity, close vicinity. So 50 degrees north. Longitude we don't know. So latitude is 50 degrees north. That means F will be 2 omega sine of 50. But what is omega? You know, this is constant, 7.29 into 10 to the power minus 5 radians per second. Sine 50. Just calculate this value. I don't know actually the value, but I have calculated it earlier. So it is 1.11 into 10 to the power minus radians per second. Or per second. Hertz. What is rho? This is also known. I am writing 1.28 kg per meter cube. It will write 1.2, 1.25, whatever. It does not change much. So these things are known. Fine. So if I do rho a, it gives you so yes 1.28, 1.11 into the power minus 4. This gives you 1.42 into 10 to the power minus 4. Just remember there will be some SI unit of density times this. Okay. Now geostrophic geostrophic wait. What should be the geostrophic? This is the question. So since only delta P delta Y exists, so we will get UG. Okay. So UG will be equal to so it should be 1 upon 1.42 into 10 to the power minus 4. Okay, 1 by rho and delta P delta Y with a minus sign. So what is delta P delta? This minus minus becomes plus 10 to the power 4. Dismiss it. Okay, 10 to the power 4 divided by 1.42 into this. If you calculate all these things, you get plus 19.56 meter per second. Plus represents eastward. So we'll get about 19.56 meter per second in the eastward direction. All right. So let's see the options. Yeah, 19.9 meter per second. They have not, although they have asked for direction, but it is not there in the options. Okay. So when you have such kind of information, check for station data or weather station data or weather station shift. Those things tells you about the local rate of change of something, some variable. In this case, it is pressure. But all other things are the total rate of change of pressure. And ship's velocities are given, so advections can be also calculated. From advection term, you calculate the gradients, and this gradients will give you the geostrophy. All right, this is a very good question, and one must appreciate this. This is a good question. Okay, so I think this completes our assignment part. Okay, so now it's done. So next we will start the week 8 content. But I, yeah, Week 8 content, particularly it will have, let me list it down, gradient wind, short. Very important after that is the thermal wind. Although you will not get any question about gradient wind or thermal wind in Week 8 assignment, you will only get questions from the ionosphere part. So after this atmospheric dynamics is over, ionosphere, space physics, and all those things will start. Okay. So mostly these are, you will get some mathematical equations, but mostly you'll see the chemistry part, physics part together. And so I will list down some points of the ionosphere from where you can easily solve. And otherwise, if you just want to learn, you can go to Google and search different things, learn different things, and try to solve the assignment question. Because the assignment questions are simple, so there is nothing much to worry. Okay. Okay. Just a small reminder that I have already pinned a link, new link. Uh, Maybe after 10 minutes it may expire because what it is showing in my full so we can join the. Okay. But till then, let us continue here. So, gradient wave. So, in the last problem solving session, we have seen uh, your natural coordinate, right? Where we have seen that there is dv dt plus 1 by rho delta p delta s is equal to 0. S hat is the direction of motion. Unit vector in the direction of motion. And n hat is the normal direction. Normal. Which normal? Leftward normal. Normal leftward to the direction of motion. So this we have already discussed, and we have already seen the natural coordinate equation. So the n hat equation becomes like this. So what it says that in the direction of the motion, you don't have any inertial terms, right? Coriolis or centrifugal. Coriolis and centrifugal forces generally act perpendicular to the direction of the motion. So that's why it comes in the normal direction. Okay. So these are the two equations of motion for in the normal sorry. Yes, natural coordinate. This is natural coordinate. Okay. So this is what you have. So what is gradient wind? Gradient wind is or is established by the is the balance, the steady state balance of pressure gradient force, Coriolis force, and centrifugal force. All the three acts together. Okay, so which equation should we use to start with? Of course, this, which have the centrifugal term, it has Coriolis term, and normal gradients of pressure. So if you just write this, V square plus R plus FV plus 1 by rho delta P delta N equals 0. Right? So if you do this, what you get? So you get V is equal to minus F plus minus, yeah, plus minus root over. So you know this is the algebraic equation. V is the variable and all others are constants. So B square minus 4 is the discriminant. So B square is F square minus 4 A. A is 1 by into C, which is 1 by rho delta P delta. Alright, divided by 2A. So 2 into A is 1 by. Right? This is how you can write. And you can solve like this. Minus A R by 2 plus minus root over R square. So R comes in the numerator. When it goes inside the root, it becomes R square. So R square square divided by 4 minus. Okay, so 4 r square by r rho delta p delta n. So 1 r cancels, so it becomes 4. Another thing is that the 4 will come. So this will go. Just check it. If you don't understand, let me know. Okay. So this is the final expression which you get. Okay. So based on this, we can have 4 conditions. So all will be existing conditions. There is nothing like that it will not exist. Like for the cyclostrophic winds, there are 2 conditions which clearly, from the mathematics, it is clearly seen that it will not be working. Okay, but here all the conditions will work. Mathematical expression is quite complicated, but if you just see this, it will be easy to visualize. See, first condition is that the r can be greater than 0, delta p delta n can be greater than 0. That means what? R greater than 0. That means wherever the motion is, yes. Mhm. Tell me. Mhm. Mhm. Del phi of del x here. अच्छा 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 हाँ हाँ ओके नहीं कुछ कंफ्यूजन नहीं है देखो दिस इज ये है जो है ना ये नेशनल कोऑर्डिनेट सिस्टम का है तुम वैसे भी लिख सकते हो कोई प्रॉब्लम नहीं है मतलब डेल्टा फाइव डेल्टा एक्स लेके लिखना चाहते हो लिख सकते हो दैट इज फाइन दोनों हो सकते हैं ठीक है तो दोनों डिफरेंट जगह पे यूज करना है मतलब अगर देखोगे कि नॉर्मल डायरेक्शन वाले क्वेश्चन है तो ये यूज करना है और अगर एक्स वाई जेड में क्वेश्चन है जैसे हम लोग अभी ये किए हैं सब कुछ जितने भी क्वेश्चन वैसा अगर है तो डेल्टा फाइव डेल्टा एक्स करना है वो जहाँ पे अप्लाई करना है समझ रहे हो एग्जैक्टली और इससे क्या होगा ये नेचुरल कोऑर्डिनेट सिस्टम जो है इससे हम लोग विजुअलाइज अच्छे से कर पाएंगे ये जो आर है जो कर्वेचर है या फिर जो प्रेशर ग्रेडियंट है नॉर्मल डायरेक्शन है उससे हम लोग इजीली विजुअलाइज कर पाएंगे इसलिए हम लोग ये यूज करते हैं विजुअलाइज करने के लिए तो देखो अभी हम लोग करेंगे ठीक है सो फर्स्ट पॉइंट इज दैट आर ग्रेटर देन डेल्टा p delta n is greater than 0 so r greater than 0 means what that suppose this is your wind okay suppose this is your wind now r greater than 0 means to the left your center will be to its left so this is how the circular isomer looks like okay so this is your r greater than 0 now normal this delta to delta which one is the normal direction leftward to the direction of motion so if this is the direction of motion go to the left this is your n hat direction in the n hat direction you are saying that the pressure is increasing because delta p delta n is greater than 0 so if your pressure is increasing here and I write here high and somewhere here low okay so where will be the pressure gradient force from high to low this should be your pg right and centrifugal force also in this direction centrifugal force will be always from center to outside, right? And where is the Coriolis force? Again, the Coriolis force will be in the same this direction. So all three are in the same direction. So in this case, there is some problem. So you cannot use this part. Okay. So all three are going in the same direction. Second thing is that r greater than 0, delta p delta n is less than. So again, this is your thing. In head direction, again in this direction, p is decreasing. So this is low. Now, where is the centrifugal force? Outside. Where is the Coriolis force? Why Coriolis force is in this direction? Because we are assuming northern hemisphere, and in the northern hemisphere, Coriolis force acts towards its right, perpendicularly to the right. So that's why. And what about pressure gradient? High to low. So see, the pressure gradient now is balancing centrifugal and Coriolis. So this exists. And you know that when you have a low pressure system, you see that the winds moves in a cyclonic direction, like this, right? Or anti-clockwise, right? So this is what you have. Third, look, this is how easy to visualize. This is the opposite one. In that, this should be like this. Center will be towards the right of it. In head direction, now is this. Left what? Normal. Wherever you are moving, left to right. This is the in head direction. P increases. So inside there is a low. So I think it will be finished now. Okay. Okay. So this is the in head direction. Now, so now this will be low. So pressure gradient is in this direction. Centrifugal is still in this because outside from the center, and Coriolis will be to its right. So this is also balancing each other. So this is an anomalous. It generally does not happen. Anomalous. Sorry. So low pressure generally has a cyclonic circulation, but here anticyclonic circulation also exists. And the fourth is R less than 0. And okay. Share the screen. Okay. Now I think you can see the screen here. Okay. So R less than 0 and delta t, delta n is now it is less than. This is the fourth one. Okay. So this is how it is looking. So R less than 0 again. So your thing is like this. Okay. So that your direction of motion is in such a way that if R is less than 0, to its right, there will be the center. The center is to its right. Okay? If you are moving over this arrow and you're moving towards this direction, towards the arrow, to its right, you are getting the center. So that is our movement field. And what is the inward direction? The normal direction is leftward normal. So if you are moving in this direction, where is your left? This. So this is your inward. In this inward direction, it is saying that delta P delta M is less than 0. That is, pressure is decreasing. So pressure is decreasing. Here it should be high, and slowly as you go outward, it will be low. So your pressure gradient will be in this direction because high to low. Next, centrifugal is also in this direction. F centrifugal. And what about Coriolis? Is in this direction, right? So it is also balanced. So this is balancing perfectly. This is also balancing perfectly. This is also balancing. But only this condition is not valid because all the three pressure gradient, Coriolis, centrifugal, all three are in same direction. So where is the balance? It's not balancing. Therefore, this condition is invalid. Okay. So this is all about the gradient. Next is the thermal. This is also very important, particularly meteorological field. So for the thermal wind, the best way to define is that the wind which blows due to the gradient in temperature. Okay, this is one of the definitions. Second definitions. Second, this is one of the definitions. Second definition is that it is the vertical shear of geostrophic wind. Vertical shear of UG. What does it mean? Simple delta delta z of UG or delta VG by delta Z. Either you can Z or you can write P in pressure coordinate. So this is Cartesian coordinate, x, y, z, t coordinate, and this is x, y, p, t coordinate. Okay. So we will be using x, y, p, t coordinate to understand the further things. Okay, fine. Let us then do that. So what is the vertical shear of geostrophic? So let us or choose let's choose x, y, p, t coordinates. Okay, let us choose x, y, p, t coordinates. Remember, we will choose an isobaric surface. Isobaric surface. So when you are using p, it is constant, right? One isobaric. Okay, forget about that. First is what is geostrophic wind? We know this very well. K cross grad P of phi. Why grad phi? Because it is XYPT coordinate, pressure coordinate. In pressure coordinate, geostrophic depends on the gradient of the geopotential, not the pressure. So component, the zonal component UG is minus 1 by F delta phi by delta Y, and VG is 1 by F delta phi by delta X. Okay, we have defined the thermal wind, that is delta delta P of UG. Let's try that. This is the vertical shear of the zonal geostrophic component. So what it will be? Simple, it will be delta delta P of minus 1 by F delta phi delta Y, which is minus 1 by F. F does not vary with P, so it can be taken as a constant, delta delta Y. And can I write this? Delta phi by delta P? Yes. Similarly, delta Vg by delta P, the meridional component or y component is this. So this will be 1 by f again. F is not a function of P, so it can be taken out. Delta delta x, delta phi by delta P. Alright, so this is well known. Also, hydrostatic equation, hydrostatic equation is delta phi by delta P is equal to minus RT by. This is the hydrostatic equation available in x, y, p, p coordinate. In x, y, z, t, it is dp dz is equal to minus rho g. Here, it is like this. Okay, look now, what we are trying to do. Delta phi by delta p is minus RT by p. Look, this delta phi by delta p is now proportional to temperature. This temperature will come from here. Since we are talking about thermal wind, that means that there must be somewhere temperature gradient associated. Where should we pick up the temperature gradient? From this delta phi by delta P, right? So this is what we will see. Just a minute. Okay. So now I will put this delta phi by delta P in these two equations and try to write. So delta Ug by delta P is minus 1 by n, of course, delta delta y, and delta phi by delta P I am replacing with this minus R P by P. Okay, this is fine. Now look, this P is the pressure, which is constant. It is not varying with y. Perfect. This is not varying with y. P is constant. Why? Because we have chosen a particular pressure level. So suppose this is the particular pressure surface P. Okay. There you are seeing that how the temperature variations are taking place. This is suppose x direction. This is suppose y direction. So this is how the temperature is varying with x or y. That is what we are trying to see. P is therefore constant. It will not change with y. If P can be taken outside, R can be taken outside, and what you get? Delta T, delta Y with positives. Okay, these are all in a particular pressure level. Similarly, delta Vg by delta P, which is 1 upon F, delta delta X of minus R by P gives you minus R upon F P delta T delta X. This is also at a particular pressure level. Next we do what is that? Simple delta Ug you keep it here, and all other terms R by F, okay, delta T, delta Y at a constant pressure, delta P by this can be written like this. Let us integrate both sides. Similarly, delta Vg can be written as minus R by F, delta T delta X at constant P, delta P by P. Together, all together, we can therefore write, or you can see it from here also, delta can we write it like this, delta Ug by delta log P, which is R by F delta P by delta Y. Similarly, delta Vg by delta log P will be minus R by F delta T delta. Hence, delta vector Vg vector by delta log P will be what? This I have plus this J hat can be write therefore R by L, delta T, delta Y, I hat, minus delta T, delta X, J hat. Okay. Now we will do some trick. I, J, K. We all know this cross product tricks. So R by F, delta T, delta Y, I hat can it be written as minus K cross J? Yes, because K cross J is minus I. So minus K cross J will be I minus delta T delta X. Can this be written as K cross I? Yes, K cross I will be J. So finally, we are getting negative sign you can take common. You are getting a K, let K cross J plus K cross. Perfect. Finally, that's what you will. Okay. Now this chain therefore will be so the thermal wind D will be equal to delta Vg, which is equal to minus R by L K cross grad E and integration delta log P from some P naught to P1. P naught is the surface and to some height. So the thermal wind becomes minus R by L K cross grad T. This will be what? Log of P1 by P naught. Remember, P1 is less than P0 because P0 is the surface. Surface at the surface, the pressure is higher. As you go up, the pressure decreases. Vt will be equal to. I will just shift it and hence take the positive sign. P0 by P. So this is your thermal wind expression. So what is happening here from the thermal wind? Suppose you have two isotherms T1 and T2. T1 is less than T2. So where is the gradient? Gradient always direct from lower value to higher value. This is graph T. K is pointing upward. So K cross graph T will be in this direction. So this is your thermal wind direction. Okay, this is your thermal wind. So again, thermal wind in northern hemisphere. This is a case of northern hemisphere. Blows in such a way that low temperature is to its left. Okay, this is important. Similarly, in the southern hemisphere, it will be opposite because F becomes negative. So that will give you to its right instead of left. Okay, so this is how the thermal wind looks like. One of the examples, one of the examples of thermal wind is jet stream. Okay, so this is so we will find that in the Earth, this is equator, and this is suppose the subtropical 35 degrees north. You will find during the winter a jet blows like this. Okay, and it moves from west to east like this. You know the temperature here is larger than the temperature over here. So this is cooler region, this is warmer region. Look, the jet blows such a way that the colder temperature is to its left. Okay, so this is the jet stream. Okay. Fine. Generally, these are seen at some 500 hectopascals level. Okay, so this completes the thermal wind part. And what else we can do? Yeah, this is fine, I think. Now, let us go to the temperature profile, and then we'll go towards the ionosphere, and we'll give you some points which will help you to solve the assignment questions. Okay, so that will be enough for today. Okay, so next thing is the temperature profile of the atmosphere. We have seen already. So let us change the color, and this completes the atmospheric dynamics part. Now, the next couple of weeks, next couple of lectures, we will be mostly talking about the ionosphere and the space physics, all these parts. All right. So let's start with the temperature profile of atmosphere. So, okay, just before going to that, let me show, let me see whether this jet stream I can show it to you or not. Let me just, so let's see, change the height to say 500, 600 feet, 500 hectopascals, which is about an elevation of 5,500 meters. Look, these are the jet stream. Okay? This violet color, strong winds, as you can see. These are jet streams. You know that to the south of it, the temperatures are larger. And as you go more towards the poles, the temperatures are smaller. So jet stream generally blows in such a way that it's to its left in the northern hemisphere, it is cooler. Okay, so yeah, this is the and similarly in the southern hemisphere, which is more visible right now, see this one is a very strong, the violet color uh, band. You see that the jet stream is moving again west to east. Okay, just if you look at the wind velocity, it's moving west to east, and you know that here in this region where the plus is there, there the temperatures are larger compared to the temperatures below this particular region, south of it. So it blows in such a way in the southern hemisphere so that to its right, that is here, you have lower temperatures. Of course, because these are the polar regions, Antarctic regions. Okay, so these are one of the what you call as the examples of the thermal wind or the jet stream. All right. So this is I wanted to show. Okay. So now let us move to the temperature profile of the atmosphere. So this is your temperature axis, and this is your height. Okay. So we have already drawn this kind of a plot where you know that there are several layers of the atmosphere. So the first layer, but the temperature decreases with height, is the troposphere, right? Next, it increases with height? Actually, there are two slopes here. First, it goes like this, and then it increases further. Okay, so let me small it. So first, the temperature decreases like this, and this. Stratosphere. From stratosphere, it decreases much to the left, that is towards lower temperature, and then constantly increases. Not constantly, I mean, it starts increasing and continues to increase. Okay, and this region is almost near 85 to 90 kilometers, where the temperature is the minimum in the atmosphere. This is about minus 90 degrees Celsius. Troposphere is where all these atmospheric dynamics and weather phenomena all can be seen. This is the stratosphere, very important, where the ozone layer is. Okay, and the greenhouse gas. This is ozone, of course, is a greenhouse gas, but the ozone generally blocks the UV rays. Okay, and next is the mesosphere, and this region is height where this transition is taking place. It's called the mesopause. So, mesosphere, the end of mesosphere or the mesopause is the region of the lowest temperature in the atmosphere. And after that, it continuously increases, which we call as the thermosphere. And within a layer from stratosphere to thermosphere, ionosphere is defined. So there is no particular boundary limit for the ionosphere, which it may change. Okay, but this is how it is. Okay, so from where you can still say that the ionosphere exists. So ionosphere, okay, it exists where the height is greater than 70 kilometers. Okay, and it is this layer is partially ionized by sun UV radiation. Okay, what is another helpful thing for in this ionosphere is that long distance radio transmission are possible due to reflective properties of ionized regions. Okay, so this is one of the advantages of the ionosphere, where the radio wave reflection, radio transmissions are possible because of there are certain regions where ion they which are ionized, and those ions have a reflective properties, particularly for the radio wave transmission. Okay, and there are several graphs which are shown in the main lectures in NPTEL. Just look all those things, particularly the solar spectrum. We will discuss later on, but yeah, all these things you must know to understand the ionospheric part. I will just keep certain certain things in this particular session, not everything. So some points, 3 points, which will be helpful for solving the assignments. So that I will try to put. Okay, so there are many layers. Okay, different layers. So layers within the ionosphere. Okay, The first one is the D layer, which is the lowermost or the lowest layer of the ionosphere. Okay, which is almost about 60 or 70 kilometers to about, say, 120, or not 120, sorry, about 90 kilometers, 90 or 100 kilometers. This is the D layer. So as you can see, 60, 70 kilometers to 90 kilometers means that it, it has this particular part. It, this particular part. This is actually your D layer. Second is E layer. This is the layer which is first discovered. Okay, this is first discovered. This is E layer. E layer is after the D layer, whatever the layer comes, that is, say, from 90 or 100 kilometers to about 120 or to 150 kilometers. Because this varies, so you cannot just say a single value, but roughly from 100 to 150 kilometers, it exists. And third are the F layer. So F also consists of F1 and F2. So let us generally write the F layers. So 150 kilometers to about 500 kilometers, uppermost layer. Okay. So this is the thing. So how these layers are categorized? So these layers are categorized by the peak electron density. Okay, peak electron density wherever you present. So suppose this is a kind of a graph you can observe. So suppose this is your ionosphere starting layer. So you see that here is a peak, then there is another peak like this. Okay, so all these peak regions of ions, these are considered as D layer. This is suppose E layer, and this is suppose F layer. Okay, so peak electron density depends, means is used to segregate different layers in the ionosphere. Okay, these, okay, what else we can see? These boundaries, these boundaries change during day and night. We will see all these things in the next session, day and night, or with season also. A very simple thing, just to let you know that, see, during the daytime, the solar radiation is there, and say different wavelengths of the solar radiation or frequency, whatever you wanted to say. So different wavelengths, different frequencies generally hits the atoms which are present, hits the atoms and molecules and turn them into large number of ions. But same thing in the night time when the solar radiation is cut off, then the production of ions or electrons are stopped. So slowly and gradually, you will see that those ions tends to recombine, and hence the ions, the number of ions or electrons decreases. Okay. So how these ions are created? So how these ions? See, when you are talking about ions and electrons also, because when you create an ion, some way some electrons will also be created. Okay. How these ions are created in the ionosphere? So there are many sources. For example, high energy UV radiation. from the sun. Then X-rays from the sun. Okay, these are important. So these collides with the gas molecules and atoms of the Earth's upper atmosphere. These collisions, when they collide, these collisions, what they will do? These collisions will knock the electrons out, will knock the electrons free from the atoms and molecules. Okay, when the electrons are knocked, then what will you get? The ions. Ions are produced. But remember one thing: even when you have so much of ions and so much of free electrons, the overall, if you look at the overall charge, is some way neutral. This is very important. Although electrons are created, ions are created, but if you look at the charge per unit area or the charge over a volume, you will see that the overall charge is almost neutral. It does not say that it is completely positive or completely negative. Not like that. Because electrons are also created, charges are also created. So those combined together gives you a neutral kind of atmosphere. Okay. Next, let us write a couple of more things. I think in the main lecture notes, you might find several plots that shows how the concentration or the density of different charge particles or ions are uh, changes with altitude, height. So I'm just listing something, say lower ionosphere, which is some kind of D layer or something. You get more of O2 or N2 or the O2 plus or N2 plus. Middle ionosphere, majorly you will get hydrogen, helium, and oxygen. You can make a plus sign also. Okay, 2 plus, H plus, 2 plus, whatever. Okay. And finally, in the upper atmosphere or upper ionosphere, you get majority will be H plus. Why H plus will be at the uppermost hill? Because its density is less. Hydrogen's density is less, so hydrogen gas will be more towards the upper atmosphere, and more denser gases are towards the lower atmosphere. Now, if you have hydrogen at the upper atmosphere, collision will knock some electrons and gives you H plus atom. So, as you go more towards the upper ionosphere, say F layer, F1, or if you go more beyond that, you get this. But O plus is the majorly found in F1 or F2 layers. Okay, this is important. F1, F2 layers, O plus is majorly found before, and beyond that, you get H plus only. So this is the very important that H plus ion can be found more or predominantly or dominantly over the upper ionosphere region. Okay. Next is let us see what are the processes which can, yeah. Huh? Yes. Yes. You will see that several reaction happen. In the next, I think in the week 9 lectures also you can see that O plus formation takes place. There are some reactions which will take place. You're right, because O2 minus those things generally forms, right? But uh, there are certain reactions you will see. Right. I know, but there are certain reactions in the atmosphere where this O plus atom might be very unstable, but exists. Okay, we will see that in the later parts. Okay. So now you have the daytime versus the nighttime conditions. So X-ray and UV provides large energy that. So the process this time writing knocks free electron from atoms and molecules. Okay, and there are large number of atoms and molecules which are being converted into ions and electrons. But out of them, some of these ions and electrons recombine, recombine to normal or neutral atoms and one. Okay. So during the daytime, essentially there is a more number of or more creation than the recombination. So more creation of ions. Because as you can see, the solar radiation plays an important part. Okay. And now if you go to the night time, at the night time, because the solar radiation is cut, so the recombination predominates. Okay. So recombination is more and hence the number of ions drop. There are certain layers like T layers disappears completely. So it disappears. Okay, some points to note. So these are some brief introduction. E region weaken and however the F layer or F region sticks. It does not weak. It does not become weak. Okay, but it splits into upper F2 layer and lower F1 layer during the daytime. At the night time it is, but at the daytime, this is also a property of day, it splits. More importantly, another thing is that near the poles, this is another point which might help you in solving the assignment, that precipitating auroral electrons. What is aurora? Auroral process? We will see it later on because there are so many weeks which are remaining in which all these processes will be taught to you. Electron. So this is the major source of ionization near poles. As you know, that aurora borealis and australis, this happens near the poles. Okay, source of ionization. What else we can look for is that we are mostly done. Lastly, so the reflection of radio waves. I have just shown it to you, but yes, Generally, just in the means the ionosphere region only this takes place. But near the poles, what happens? The entire these layers, the ionosphere layers and all these layers, this generally comes down. Even if you look at the tropopause, that or the tropospheric layer, it shortens. So entire thing shortens. The entire atmosphere over the polar region, it actually decreases. And because of that, it looks like, yes, right. All these things generally comes down. So, and as a result, you see it over this region. But yes, ionosphere, mostly near the ionosphere, only this auroral phenomena occurs. Mostly not gravity, but it is the magnetic effect of the Earth which plays an important role. We will see that. Okay, later. Not in this week, maybe. Okay. So one diagram which I wanted to show, since there is time. So it's just how the reflection of radio waves happens by the ionosphere, although it is there in the lecture. So different layers. Suppose you have F layer, then you have E layer, okay, and there are several other layers. So you can see that reflection can take place. That is also depends on the ions which are present, okay, and to a large distance, the radio waves can be transmitted. So 3,200 kilometers, and this is about 1,800 kilometers. So different layers have different transmission limit. Okay, so this is about E layer, this is about F layer. Okay, and it depends on the critical frequency, which is the F naught. See, this is also based on the number of electron, the electron density. Okay, so which is in generally per centimeter cube, and the F naught comes with megahertz. Okay, so this is the critical frequency above which it will give you this reflection. Okay, next thing, another point to note for the assignment solving part is that solar activity and sunspot numbers. Okay, so when there is the peak solar activity, what is this solar activity? We will see it later. Right now, just know that solar activity and the sunspot numbers play a critical role in governing the electron. Okay, and this solar activity or this sunspot cycle is a 11-year cycle. Okay, so when you have a solar minimum, in general, within 11 years, after 11 years, it peaks. Okay, so it's a 11-year cycle. So if suppose some year, say 1994, suppose this is might not be true, but suppose 1994 is minimum, solar minimum, then say after a couple of years, like 2000, roughly half the 11 years almost. So it will be the concentration of or the Ne will be larger than the 1994. Okay, yeah, this will be I think enough to solve the question for. Hmm. No. Free electrons are present and ions are present. It is not a bound charge kind of a thing. Overall, it is neutral, right? Yes, yes, yes. Yeah. Uh, if you want to have more information about the ionosphere, see, this ionospheric part is not particularly my domain because I have always worked in the atmospheric dynamics part, which is related to the troposphere. But if you want more information, you can go to uh, the the previous course of this advanced atmospheric physics, that is uh, Introduction to Atmospheric and Space Sciences. There you will find detailed information about this ionosphere part. This is a related aspects as well. Okay. Hmm. Yes. Right. No, no, it's a simple thing. It's a simple thing. See, during the daytime, reason is that the solar radiation comes and the energy at a particular frequency, suppose some ions or some gases are prone to uh, get separated or ionized based on some X-rays, suppose X-rays of the sun. Some ions or some gases, yeah, some gases will use UV rays to separate out. So in this way, it will try to produce ions. But at the same time, there are certain reactions which try to help them recombine. These ions and electrons again gets fused to form another gas molecule. So this recombination and production, these are continuously happening, parallelly happening during the daytime, of course, the production is much more compared to the recombination. But in the night time, since the solar radiation is completely cut off, the production completely stops, but recombination starts dominating. That is the clean point. Yes, yes, right. Okay, fine. So I think this is enough today. Maybe we can stop because whatever information I have provided, it's perfect for the assignment solving because I can see the week 8 assignments are mostly based on the ionosphere part. But yeah, also we have seen the thermal winds and the gradient wind balance, natural coordinates, and also solve the assignment 7 questions. Okay, so fine. We will stop here and maybe we can meet in the next session. Tuesday. Okay, okay, bye. Thank you.